In the era of challenges far beyond our atmosphere, a single material has fundamentally changed the game. Welcome to the heart of carbon fiber engineering and manufacturing. Lighter than aluminum and stronger than steel, carbon fiber is the silent revolution powering our modern world and the future of interstellar travel and deep space exploration. This is where chemical magic transforms simple polymers into the very backbone of spacecraft, creating structures that can withstand the harshest environments found in the dark universe. Our journey begins at the first station, where state-of-the-art robotics handle the delicate raw materials that will soon become the strongest substance known to modern aerospace engineering. Watch closely as we unveil the complex process of turning soft white threads into the rigid, black skeleton of future aircraft and rockets destined for the stars. Everything starts with polyacrylonitrile, or PAN. These delicate white polymer fibers hold the potential molecular structure needed to build the next generation of high-performance space vehicles. The tension must be absolute. Each strand, significantly thinner than a human hair, is carefully guided through a series of rollers to ensure perfect alignment and structural integrity. Purity is paramount. The fibers pass through a specialized chemical cleaning system to remove every microscopic impurity, preparing the polymer for its dramatic transformation in the thermal chambers. Advanced sensors monitor every micron of the process. In this high-tech environment, consistency is the key to creating a material that can survive the vacuum of space. The sheer scale of the Creole room is breathtaking. Thousands of individual threads come together, yet moving as one toward the furnaces where their molecular fate will be sealed. Speed and tension are perfectly calibrated. This mechanical ballet ensures that every inch of the precursor material is ready for the intense heat that lies ahead in the ovens. As the white fibers disappear into the first furnace, they leave behind their polymer origins. A new, much stronger structure is about to be born through controlled oxidation. Oxidation is the first critical transformation. Under strictly controlled temperatures, the PAN fibers begin to react with the air, changing their color and internal chemical bonding structure. The temperature is managed with extreme precision. Even a few degrees of deviation could ruin the entire batch, as the molecules must reorganize themselves at a specific thermal rate. Inside the fibers, a microscopic dance occurs. The linear polymer chains start to close into stable rings, creating a ladder-like structure that provides the foundation for heat resistance. The transformation is visible to the naked eye. What started as soft white plastic has become a bronze-colored precursor, now capable of withstanding much higher temperatures in the next stage. The heat is relentless but calculated. Every strand must be baked evenly to ensure that the chemical conversion is consistent across the entire width of the fiber sheet. As the brown color deepens, the fibers become thermally stable. They are no longer simple plastic. They have evolved into a precursor that can survive the intense carbonization process. Massive ventilation systems maintain the perfect environment. This complex balance of heat, air, and tension is what separates ordinary materials from the building blocks of aerospace legends. Expert eyes monitor the process constantly. Human intuition and machine precision work hand in hand to ensure that the chemical metamorphosis is proceeding exactly according to the design. Now dark and resilient, the fibers are ready for their ultimate trial. They move toward the carbonization furnaces, where temperatures will soar to levels that would melt most metals. To reach the next level, we must eliminate oxygen. Massive tanks of pure nitrogen provide an inert atmosphere, preventing the fibers from burning up in the extreme heat. Enter the carbonization stage. In this oxygen-free environment, the fibers are subjected to temperatures exceeding 1000 degrees Celsius, driving out all non-carbon atoms from the structure. Under this incredible heat, the material is purified. Hydrogen, nitrogen, and oxygen are expelled as gases, leaving behind a dense and incredibly strong network of pure carbon atoms. At the atomic level, carbon atoms align into hexagonal sheets. These layers stack together like microscopic armor, thus giving the fiber its legendary strength-to-weight ratio and mechanical stiffness. What emerges is true carbon fiber. It is now jet black, sleek, and incredibly strong. It passes through a cooling zone to stabilize its new, hardened atomic structure. Rapid but controlled cooling is essential. The transition from intense heat to room temperature must be handled carefully to prevent any internal stresses from weakening the carbon strands. The transformation is complete. These black ribbons are now the strongest material produced at this scale, ready to be integrated into the most advanced machines on Earth. The physical properties are now set. The carbon content is nearly 100%, creating a material that is virtually immune to corrosion and incredibly resistant to stretching. Hear the sound of strength. The fibers now have a metallic ring to them, a sign of their extreme rigidity and the high-quality carbon structure created within. Quality control is continuous, and every millimeter is scanned to ensure the carbonization was perfect, guaranteeing that the final product will meet the rigorous standards of aerospace engineering. Strength alone is not enough. The fiber must be able to bond. Surface treatment through electrolysis creates microscopic roughness, allowing the fiber to grip the resin in later stages. A protective coating, called sizing, is applied next. This thin layer of resin protects the delicate fibers from damage during the weaving process and improves chemical compatibility. Precision rollers ensure the coating is perfectly uniform. Not too much, not too little. The exact amount of sizing is critical for the final material's composite performance. Infrared heat quickly dries the protective coating. The fibers are now shielded and lubricated, ready to be wound onto spools or sent directly to the massive looms. The finished fibers are wound onto spools with perfect tension. Now, these bobbins of black gold are now ready to be shipped to weavers or composite manufacturing plants worldwide. Each spool contains kilometers of continuous carbon fiber. It is a material that combines the flexibility of a textile with the strength of a high-performance structural metal. Automation ensures that the fiber is never touched by human hands, maintaining its absolute purity and integrity from the start of the process to the very end. In the weaving hall, the individual fibers are transformed into fabric. High-speed CNC looms interlace the black strands into beautiful, strong patterns like twill and plain weave. The pattern is not just for aesthetics. It defines how the material will handle stress. Weaving these fibers together creates a multi-directional strength that is impossible with solid metals. Laser precision is used to cut the fabric into exact shapes. This ensures that every piece fits perfectly into the molds used for aircraft wings and high-speed satellite components. Yet the human touch returns as experts layer the fabric into molds. This hand-laying process ensures that the fibers are oriented exactly where the maximum structural strength is needed. The parts enter the autoclave, a giant pressure cooker. Heat and pressure fuse the fibers and resin into a single indestructible composite structure that defines modern aviation. From the wings of the Boeing 787 to the chassis of Formula One cars and the hulls of SpaceX rockets, carbon fiber is the essential ingredient for speed. The final result is a masterpiece of engineering. It is a material that is as beautiful as it is functional, representing the peak of human material science achievements. Nothing is left to chance. Every component is scanned with high-resolution cameras to ensure that it is ready for the extreme pressures of flight and the vacuum of space. The innovation never stops. In research labs around the world, scientists are already working on the next generation of carbon materials, aiming for even greater strength and lightness. We are pushing the boundaries of what is possible. By understanding the very atoms of carbon, we are unlocking the secrets to building cities in the stars. Carbon fiber is more than just a material. It is a testament to human ingenuity. It is the thread that weaves our dreams of space travel into reality. A new aerospace era is being woven right now, one black strand at a time. Thank you for joining us in the world of high-performance carbon fiber.